Very good.
Hi, everybody. Welcome to Wednesdays at NICO this week. It's my great pleasure to introduce Zhimei Ren, who's a rising star who's broadly interested in theoretical and applied statistics topics, including multiple hypothesis testing, survival analysis, distribution-free inference, and data-driven decision-making. Zhimei earned her PhD in statistics from Stanford University, and she's currently a postdoc at the University of Chicago in the statistics department, working with Rena Barber. But starting this summer, she'll be starting her first faculty position as an assistant professor in the Department of Statistics at the Wharton School in the University of Pennsylvania. So without further ado, please join me in welcoming Zhimei Ren.
Thanks a lot for the nice introduction, and thanks a lot for having me here today. I am excited to share with you my recent work on how to effectively learn a policy with offline data and without the overlap condition. So this is joint work with my wonderful collaborators, Ying Jing from Stanford Statistics, Joran Yang from Yale Statistics, and Jaran Wang from Northwestern IMS. So, wow, is this working? There we go. So in a lot of areas, we actually wish to provide solutions that are tailored to individuals such that it optimizes the overall outcome for a population. For example, in precision medicine, we wish to provide individualized treatment or individualized medicine for the patients for certain diseases. So here we might want to ask the question, given a patient's characteristics, can we provide the best treatment rule for that individual? So let me give you another example. In recommendation systems, we might have the information on the user's digital footprint. And the question to be asked is, what kind of product should we recommend to that user based on that user's digital information such that it optimizes some outcome we have in mind, for example, purchase rate or other things that you might be interested. So for all these kind of questions, what we're really looking for is a mapping from the characteristics of individuals to an action to be taken. For example, in the precision medicine case, the characteristics can be the genetics of the patient, the medical history of the patient, so on and so forth, and the action is the medicine to be prescribed or the treatment to be used on that patient. And what we're looking for is, can we determine what action is the best one given the individual characteristics? So in order to learn these kind of optimal policies, we need data, right? There are multiple ways to get these data. An obvious, perhaps intuitive way to learn this policy and get data is to do online experiments, meaning that we use some policy at first, we assign that to some people, and then we get the response, and then based on the response, we tune this policy a little bit in a way that we think is going to improve it, and then we assign that policy again to the next batch of people, and then get response and refine it, so on and so forth. So this is online experiments, but this is ideal to do, but it's not very feasible in most of the times. For example, it could be very costly to do online experiments because often in the early phases, your policy is not very effective, so it could cost you a lot. And it could be unethical to do so, especially when it comes to, for example, medicine or clinical trials. It is just unethical to do online experiments. On the other hand, we have large amounts of offline data. So here by offline data, I mean the data that has been collected a priori by other people from other experiments. For example, the data from adaptive experimental data that are used for other purposes. So for example, we have some data from a company that's used for their purpose, but we want to learn a best policy for our purpose. So can we utilize that offline data? Another example is the log data from a recommendation system. So the companies have all these kind of data. So the question to be asked in this project is that given some offline data that has been collected a priori, can we learn an optimal policy using this offline data? Meaning that we don't have the ability to tune this data that is to be employed on the population. Okay, to study this problem, we consider the contextual bandit framework, where there is we use the vector X to represent the user's characteristic. And then given that characteristics, an action is to be taken by the agent. So here we consider a set of actions, A1 to AK. So for example, we can think of those as K kinds of treatment or K kinds of drugs, K types of products to be recommended to the users. And then after taking this action, there is a reward from this person. For example, the outcome of a disease, the survival time of that patient, or whether the user purchased or not. So the reward is going to be a function of both the characteristic of the user and the action made by the agent. And for convenience, we're assuming that the reward is a real number bounded by 0 and 1. It's just very easy to relax this assumption. And we are assuming that the characteristics of the patients are sampled from some distribution P of X. We're not assuming that we know this distribution at all. And then the outcome of that individual Y is sampled from this distribution, mu of X and A plus some independent mean zero noise. So here, mu of X and A is the mean outcome function, which is depending on X, the characteristics of the individual, and A, the action. Okay, so now we have set up the model. Then how is the offline data collected? So let me just characterize the data collection mechanism for the offline data. So here we can consider a wide range of data collection mechanism. For example, if the data is collected by some bandit algorithms, or they're from some adaptive experiments, or they're just from some fixed logging policy, meaning that we just use one policy throughout to gather the data. So to be more specific, under our framework, let's consider a time horizon t. At each time point, there is one user arriving. And then at point 1, a user 1 arrives, and that user's characteristics is represented by this x1. And the agent, looking at these characteristics, chooses an action a1. And then after, based on this characteristic x1 and the action a1, there is a reward for that user, that is y1. So this is the first step. And then we have this information. We are using this h2 to represent everything that we have seen before second step. And then at the second step, another user arrives, represented by this x2. And the agent now have seen everything that has happened in the first stage, can use this information to determine the action to be used on user 2. So this is A2. So A2 is not simply a function of X2, it is a function of X2 and historical data. So we do this sequential kind of data collection mechanism, and then so on and so forth. And at time t, we have all these previous information HT from time point 1 to time point t plus 1, and the agent at time t can use all the information to determine the action to be made on that user. So this is a typical scenario that would happen for bandit data. Yes, please.
This is describing the data.
Exactly.
So, yes, basic question. Data collection. Or is it preparation?
Yeah, that's a very good question. So this is this is the offline data. So there's nothing happening in so the hypothesis testing or learning is not happening in this stage. This is just a way of describing what is a typical way of data collection in practice. So if the data is collected in this way, we're able to utilize that data set collected with this mechanism afterwards. Yeah, thanks for that question. Do we have other questions? Right. So yes, this is our data. So we're using this D to represent the N triplets, X, C, A, T, Y, T. So this is the data that we're going to use for our purpose. And here we are making a few assumptions. First, the XT, the characteristic vectors of the individuals, we assume that they follow an ID distribution. From their ID sampled from a distribution P of X. You can think of independent ID users arriving sequentially. And then we are defining this function of treatment assignment mechanism, the probability of the agent choosing action A given history and the characteristics of that individual being X. So we are assuming that this quantity is known because in most of the cases, there are some people or agents designing experiments. So this information is typically known to us. And then YT, the outcome is from a distribution, is from a mean function plus epsilon noise. So this is our assumptions. Okay, next, let me just describe a few specific scenarios under which, yes, please. For sure.
That the space of possible actions is same?
Yes. No, the possible actions, the set of possible actions is the same throughout the time, and it has a finite number. Yeah, thank you for that question. Okay, so there are multiple practical scenarios we come across this kind of offline data collection mechanism. First, when we have batch data, meaning that the treatment assignment mechanism stays the same throughout the experiments, and then the function ET of X of A is just the same function throughout. And as a result of this, we have IID data that is independent across time. This is one example, a simple example. More complicated example is the adaptively collected data, where this ET of XA, given the history, is not the same across time. So we might the agent might be changing their policy of assigning actions or assigning treatments across time. So because they are able to use the information that they have seen before, there might be dependence across T. And also, if you think of Thompson sampling or a bandit algorithm, they might have, because they want to minimize some regret over time, so the algorithm might commit to one of the arms that they think are optimal at the end of the experiment. So we will have very imbalanced ET of XNA given HT towards the end of the time horizon. So these are two typical examples that fall into our framework. And our goal is to learn a good policy with the offline data collected with the aforementioned offline data collection mechanism. So as I mentioned before, a policy is a mapping from the characteristics to the action. So what is the optimum policy? We need to define the metric that in order to evaluate these policies. So the metric we're using is called the policy value. So intuitively speaking, it is just the average outcome in a population if we were to deploy this policy on that population. So it's just the expectation of the mean function of the outcome over the distribution of X when we take the action according to this policy pi of X. Okay, this is called the policy value. And then we restrict our attention to a policy class. So in order to find the optimal policy, we mean that we are to find the optimal policy within a class of policies. So you can think of this class of policy as the class of all linear policies, or the class of all tree-based policies, or the class of all neural network-based policies, so on and so forth. And the optimal policy in this policy class is defined to be the policy that maximizes the policy value resulting from deploying that policy on this population. And with the offline data, we will learn a policy pi hat, and we wish that this pi hat has a policy value that is as close to the optimal policy value as possible. So we're using this gap out of pi hat, which is the difference between the optimal policy value and the policy value of the learned policy, as the thing that we wish to minimize. Okay, so this is our learning goal. So typically, when we need to learn this optimal policy, people take a two-step greedy procedure. So in the first step, you would imagine that we would use the offline data to construct a point estimate for the policy value of a given policy, right? And then the second step, we're just going to maximize this estimate value of the policy estimate value of the policy value, and then take the policy that optimizes this estimation as the one that we think is optimal. So in order to make sure that this greedy approach gives you a good answer, meaning that the greedily learned optimal policy is actually close to the optimal policy, people usually need to impose the uniform overlap assumption, meaning that the infimum of the treatment assigned probability for each of those arms should be lower bounded by something. In the batch case, it's lower bounded by some constant eta, or in the adaptive case, it's bounded by some function of t. So this might be a little bit complicated, but intuitively, it just means that we need to ensure that all the possible pairs of X and A has been explored well in the offline data, such that we can have a good estimate for the policy value of pi uniformly. So here is a list of prior works that have been considering this problem of policy learning with offline data. It starts with the batch data, meaning that we have IID data. There's no temporal dependence. And then they're assuming the overlap condition, meaning that the minimum propensity score, the probability of assigning a treatment, is lower bounded by some constant. And then they're considering only two actions. And later, this is generalized to the case where they have multiple actions, but it's still using batch data, and there's the overlap condition. And recently, there have been works that consider the adaptively collected data. So now we're allowing temporal dependence, But again, there's the overlap condition, meaning that the probability of assigning a treatment is uniformly lower bounded by some function. Okay, so this is the state of art techniques, existing works. So it seems to us that the greedy algorithm and the uniform overlap condition is essential or is standard in the literature of policy learning with offline data. Let's take another look at the uniform overlap condition and see whether they are actually practical at all. So remember that in the batch case, we need the E of xt to be lower bounded by some constant eta, and in the adaptive case, we need the infimum of ET of xa to be lower bounded by some function of t. So for the batch data, suppose that your logging policy is some expert policy designed by some human that gives a very large weight to some treatment, but small weight to the other treatment. You have a very imbalanced data set. You don't have this, you probably don't have this condition satisfied. Or some of the arms substantially more expensive than the others. Again, you want to avoid those arms when you're doing experiments. So the data you have is also imbalanced. So this problem might be more pronounced in adaptively collected data case because the agent has the ability to gradually tune that policy. So towards the end of the time horizon, they may be committing to some of the arms that they think are substantially better than the others. So some of the arms just rarely get pulled, so the data would be extremely imbalanced. And so thinking of these practical situations, it seems to us that policy learning is ruined by these actions that are rarely taken, even if they are suboptimal arms. So we ask this question whether the uniform overlap assumption is really essential for efficient policy learning. And in this work, we're giving the answer, not always. We are actually able to achieve efficient policy learning even if the uniform overlap condition fails. Okay, so as I said, we're going to relax the uniform overlap condition so to still enable efficient policy learning when the uniform overlap condition fails. So in this work, how we achieve this is by introducing this algorithmic change, where instead of taking the greedy approach, now we're taking this pessimistic approach. And then the guarantee that we're able to achieve is that the suboptimality gap, which is the difference between the optimal policy value and the learned policy value, only depends on the overlap condition of the optimal arm, optimal policy, meaning that if the optimal policy is explored well in your offline data, even if some of the suboptimal arms are never pulled at all in your data, we still can learn well. So if you look at this plot, what I'm plotting is the probability of applying, the treatment assignment, or I call it the propensity score for the policies. And the red line is the propensity score for the optimal policy, and the blue line is the propensity score for the infimum of the propensity scores. So these are very different. If we're allowing our suboptimality gap to depend on the red one, it's a very good case. Whereas if we're allowing, if the suboptimality gap depends on the blue one, it's actually very bad. So we can see this is a huge difference between our theory and the previous theory. In order to achieve this, we also introduced a new analytical tool for establishing this result. It's called the generalized empirical Bernstein inequality. So due to time constraint, I'll be focusing on the first two parts of our contributions. And for those of you who are interested in the inequality, you can check out our paper. So before I dive into the details, I'll just going to pause for a while to see if there is any question. Yes, please. Mm-hmm. E sub t, it is a probability. Right. Exactly. Exactly. Yeah. Right. given x, pi of x is of action, it's fixed. And then ET of x pi x is just the probability of taking the action pi of x given x. So pi of x is just like one of those actions. It's not a probability measure over the action space.
That states that
Right, right.
because of that.
Exactly, exactly. Because I'll explain this a little more in the coming slides. Basically, the idea is when we're doing greedy learning, we need to control the error everywhere. So we need to have a good estimate everywhere. So we need to explore all the possibilities as well. I guess it's the overlap between the target policy and the like the state's well, the target policy and the behavior policy. The behavior policy is the policy that you use to collect the data. So if there's overlap, meaning that the thing that you actually want to evaluate appear in the data set that you have. So it's called the overlap. That's my interpretation. Yeah, thanks a lot. Do we have other questions? Okay. So yeah, in part one, let me just explain why the uniform overlap condition is so important for the greedy learners, and hopefully that is going to give us some intuition why we need to do this algorithmic change. So like as I explained before, typically how people do this greedy learning is first construct a point estimate and then optimize this point estimate. For the point estimate, a typically used estimator is the unbiased inverse propensity weighting estimator or other variants of it. Basically, if we want to evaluate the policy value of pi, we look at the offline data set and only take those, the idea is only to take those data points such that AT, the actually used action, equals to pi of xt. But because of this selection, there is a bias if we're using this subset of data, right? So the idea of IPW is just to reweight these data points by the inverse of this ET function, such that it's an unbiased estimator for the policy value of pi. This is the typical estimator used for evaluating the value of pi. So if you look at the form of this estimator, you would imagine that a small value of this ET, I call it the propensity score, would cause a large variance of this estimator, right? So let's look at this plot here. I'm thinking of a very, very simple case where there are only two arms. And then the left, this is a multi-arm bandit problem. The left-hand side is better than the right-hand side because Q of pi 1 is greater than Q of pi 2. So that's their mean. But the left-hand side arm is explored well. It has lower variance. So the realized estimator Q hat of pi 1 is concentrated around this Q of pi 1. But on the other hand, for the second arm, because it's not explored well, so when estimating the policy value of the second policy, there is a high variance. So the estimator of pi 2 could be jumping around. So in this plot, we see the Q hat of pi 2 is actually up there. So when we're doing greedy learning, we're actually going to choose pi 2 instead of pi 1 because of the high variance that appears in this plot. So what it means is that, if we were to make the right choice, we need the estimation error for pi 1 and pi 2 to be uniformly controlled so that we don't make this kind of mistake. So that's why uniform overlap condition is that important for the greedy learning method. So now let's take a closer look at the suboptimality gap for the greedy learner. So the suboptimality gap is the difference between the optimal policy value and the policy value of the greedy learn policy. And then we can decompose it into three parts. The first part is the estimation error of the optimal policy. So it's fixed and it's unavoidable. It just depends on how well this policy is explored in the offline data. And the second term is just the estimated policy value of pi star and the estimated policy value of pi hat. So this is the optimization error, because when you're doing a good job in optimization, the Q hat of pi hat should be minimizing the Q hat of pi over all the pi. And the third one is the hardest. It's the hardest to control because it's the estimation error of pi hat, which is a function of the data. Because like bad policies may appear good because of a large variance. And the previous example that we see is that we essentially need to control the maximum of the estimation error in order to make sure that the third term is small. So this scenario also happens in empirical risk minimization framework. So to translate that into the overlap condition, it means that we need this function E of xt pi of xt given ht to be sufficiently large for all of those policies. And suppose that this policy class is rich enough, it essentially says that we need this infimum over all x in A of E of xa to be lower bounded. This is a very stringent condition. So how are we going to avoid this condition is by introducing this pessimism principle. Suppose now we have this ability to construct a function of pi, we call it r pi, such that it upper bounds the gap, the estimation error of pi for all of those pi's in this policy class with high probability. So if suppose r pi is a good estimator for the estimation error of pi, and then what we're going to do is that instead of optimizing the estimated policy values, we're going to maximize the lower confidence bound for the policy value. So here, because we're assuming that r pi is upper bound of the estimation error of q of pi, so q hat of pi minus r pi is a valid lower confidence bound for all of those policies. Now we're not optimizing the estimated policy values, we're maximizing the lower confidence bound. So this is called the pessimism principle. Just to be more graphical, this is a plot. The dashed line represents the true policy value, and the solid line is the estimated policy value. And then, as I said, we're going to construct upper and lower confidence bound for these policy values. So the red line, the red solid line represents low confidence bound. So if we're doing greedy learning, we're going to choose the left-hand side point that is maximizing the estimated policy value. But if we're doing pessimistic learning, we're going to choose the one on the right-hand side that's maximizing the lower confidence bound. So there are different cases. So if we have a high estimate value, but a high uncertainty, we're not going to choose it by the pessimistic principle. If we have a low estimate value and a high uncertainty, definitely we're not going to consider it. If we have high estimate value and low uncertainty, good, that's where we're going to choose it. And most importantly, when we have a reasonably good estimate value, but low uncertainty, we're going to choose it. So I guess the first case and the fourth case best distinguish the original greedy learning framework and the pessimistic learning framework, because originally we're going to favor the first case than the last case. But now under the pessimistic framework, we're going to favor the fourth case because we're penalizing the high uncertainty here. So what's good about this pessimistic policy learning is that if these R of pi are indeed good upper bounds for the estimation error of Q of pi, we're able to show that the suboptimality gap of the pessimistic learner is upper bounded by 2 times R of pi star, where pi star is the optimal policy. It's not it's not the supreme over all the policy. It's just a function of the optimal policy. And here, because you can think of R of pi as an estimate for the estimation error of policy pi. So we will see that the suboptimality gap is going to be small as long as this optimal policy can be approximately accurately estimated. Let us just compare with the original greedy algorithm again. So in the greedy algorithm, the guarantee that we have is that if we're able to show that if there's a R, which is not a function of pi, is upper bounding the estimation error for all of those policies, we have that the suboptimality gap of the greedily learned policy to be upper bounded by 2 times R. And for our pessimistic approach, if we're able to show that this R of pi is upper bounding the estimation error of pi, then our suboptimality gap for the pessimistic learner is upper bounded by the estimation error of the optimal policy only. In other words, the greedy learning method is actually optimizing an uninformative lower confidence bound. So because the confidence, so the uncertainty quantification is not a function of pi. So basically, Q hat pi minus R is also a valid lower confidence bound, but it's just not a function of pi. We're just not using that information at all. So when you're optimizing this Q hat of pi minus R, it's just equivalent to optimizing this Q hat itself. So this is not using the information of uncertainty quantification for each of those pi's. So, okay, that's the pessimistic framework. So before I go into details of how we construct these lower confidence bounds, do we have any questions? Okay, great. So next, I'm going to show you a little bit how we construct these lower confidence bounds. So first, again, we need to construct a point estimate. So in our framework, we're using this augmented inverse propensity weighting point estimate. So it's just a variant of the previous IPW estimator. We're just allowing some more flexibility. So here, Q hat of pi is a summation of, it's the average of this gamma hat T of pi, where gamma hat T is of this form. And Q hat of T is just some estimate of the mean function. And in the IPW case, it's just 0 across time. This is an unbiased and consistent estimator for the policy value of pi. And this is also standard in the causal inference and policy evaluation literature. So for simplicity, you can just think of this mu hat of T as 0, which is the IPW estimator. So having these point estimator at hand, now we need to do the uncertainty quantification. So if you look at the form of this point estimate, you would think of that the estimation error to be approximately the variance of the estimator because they're unbiased. So the idea for constructing these R pi is to approximate the variance of the estimator Q pi. So to be more specific, R of pi is going to be a constant beta times V of pi, where V of pi is now a maximum of the 3 terms. What are the 3 terms? It's actually the first term, we can think of it as the sample variance. And for the second term is just the population, the sample standard deviation. And the second term is just the population standard deviation. And the third term is just some higher order error that's typically bounded by the first terms. So basically, we are using the maximum of the sample standard deviation and the population standard deviation to be an estimator for the estimation error of the policy value of pi. Okay. So for this type of R of pi, so how does it work? Does it give us a valid bound on the estimation uncertainty? So actually, we can show that the Q hat of pi minus Q pi, which is the estimation error of pi, would be approximately bounded by the complexity of the policy class times that V of pi, which is the estimation of estimation error for evaluating Q of pi. So the specific theorem that we have is that suppose that we take this R of pi to be beta times V of pi. Remember that this V of pi is just the maximum of the three terms, the sample standard deviation, the population standard deviation, and the higher order term. And this beta, you can just think of it as something proportional to the sample complexity of this, the complexity of this policy class. Where now we're using the term Natarajan dimension to measure the complexity of this class. So when we have only two actions, this is just the VC dimension of the policy class. So if we take R pi to be this thing, we can show that with probably at least 1 minus delta, the estimation error of policy value of pi is bounded by beta times V of pi. So it's approximately complexity of the policy class times the standard deviation of the point estimator. Okay, so that's the upper bound for the estimation error. And because of this, using the pessimism principle, we can show that the suboptimality gap of our pessimistic learner is going to be bounded by beta times V of pi star. Remember, beta is proportional to the complexity of the policy class, and V pi of star is just the standard deviation of the estimator for the optimal policy. So what's the message here is that if we have batch data and then the optimal policy has been explored well in your offline data, we are able to achieve good suboptimality gap for our pessimistic learner. And we actually don't need to know whether this optimal policy has been explored well a priori, because when we run this algorithm, we don't need any information on this. But this, if this is the optimal policy is actually explored well in the offline data, it's just honestly reflected on the suboptimality gap that we get in the end. So this is fully data dependent and optimal in the sense of minimax optimality. Okay, next, if we have adaptively collected data, the story is similar. We can also derive an upper bound for the estimation error for the policy value of pi. And the upper bound has the same form, where beta is proportional. It is a function of the complexity of the policy class, and V of pi is just the standard deviation of the point estimate of the policy value of pi. And as a consequence of this, we're able to show that if with this choice of beta and with this choice of a V of pi, the suboptimality gap of the pessimistic learner is upper bounded by beta times V of pi star, which is this complexity of the policy class times the standard deviation of the point estimate for the optimum policy. So again, we don't need any boundedness assumption to achieve this result. And then this is fully data dependent in the sense that we don't need to know whether the optimal policy has been explored well a priori. They're just honestly reflected on the bound that we get in the end. Okay, so let's look at a more specific case where we're assuming that the propensity score for the offline data is decaying at a polynomial rate, meaning that we're assuming that E of t is lower bounded by t raised to the power of minus beta. So for the result in the literature, existing result, we need the infimum of all those ET of XA to be lower bounded by t times minus beta, such that we can upper bound the suboptimality with the square root of the Natarajan dimension of pi divided by t to the 1 minus beta. For us, we only need the propensity score for the optimal policy to be lower bounded by t to the minus gamma to achieve the same rate. Meaning that if the condition in A does not hold, our condition B might still hold. And if our condition A holds, our condition also holds. So basically, we are discovering a wider range of applications where efficient policy learning is still possible, whereas the previous literature does not have this kind of results. Well, in other words, policy learning is not necessarily ruined when the uniform overlap condition does not hold, as long as the arms that you're discarding are not optimal ones. So let's go back to this plot. This is a scenario where there are more possibilities of efficient learning. As I mentioned before, in these two cases, the red line is a good scenario, whereas the blue line is a bad scenario. So previous result says when we have this kind of scenario, we are doomed. We cannot do good. But our result said even if you have this scenario, as long as the red line is up there, we are still able to do efficient policy learning. So basically, the take-home message is that there are more scenarios where efficient policy learning is still possible. Okay, so I think I'm good on time. Just a summary. In this work, we propose a new algorithm that's optimizing the lower confidence bounds for the policy values instead of optimizing the point estimates of the policy values. So this is called the pessimistic principle. So sometimes being pessimistic is good. We also developed some concentration inequalities for policy evaluations without the boundedness assumption, which is often needed in the literature. And the most important story is that we are able to do efficient policy learning even when the uniform overlap condition does not hold. As long as the overlap condition for the optimum policy is there, then we're in the good shape. So for those of you who are familiar with the literature in bandits, we know that in online bandits, people use the principle of optimism to guide exploration. But for offline data, the story is switched. We should now use the pessimism principle to adapt to the uncertainty of the data, because now we don't have the ability to tune the policy. We don't have interaction with the environment. So the policy is exactly the opposite. I guess this work proposed more questions than that it solves. There are a lot of remaining things questions that can be done. So for one, this work is more of a theoretical investigation of this policy learning when the uniform overlap condition fails. But how to efficiently carry out the optimization step actually poses a very challenging problem, because now, for example, if our policy class is based on trees, how do we optimize the lower confidence bounds in an efficient way is actually a non-trivial problem, and it could be very interesting. And other extensions of this work could be from bandit to sequential settings. For example, what can we also use this kind of principle for reinforcement learning? That could be very interesting. And can we extend this to other reweighting based method? That could also be extensions of this work. So yeah, with that, I would like to thank you for your attention. Happy to take questions. Thank you.
Thanks for the interesting talk. So here's, maybe you answered this, but I'm not sure I got it. If the overlap condition is actually satisfied in offline data, you use your pessimistic approach rather than the greedy algorithm. How did the results inevitably agree or not? I'm not.
They agree.
They agree.
They actually agree. Yes.
Okay. So yours is really a generalization then. If you get the same results with the overlap condition, but it also works.
Exactly. Yes. Yes. Thank you.
I can ask. Other totally different question. So you use expected value optimization, I guess, as a starting point. But what if you have outliers? I guess the medians, I guess, a less volatile estimate of data in that case. So what carries over if you wanted to use medians rather than means?
Oh, that's a really interesting question. Yes, I think the pessimism principle can still go through, meaning that we can still construct lower confidence bounds for, say, the quantile of your policy value or something. But constructing that lower confidence bounds might need substantial work because like now our whole story is centered around estimating the mean using the concentration inequalities to establish that uniform lower confidence bounds, but more things needs to be done for constructing that low confidence bounds. Yeah, but that could be very interesting. Thank you. Yeah, please go ahead.
Yeah, so since you get the optimal policy, if it using both the greedy algorithm and the pessimistic algorithm, if the optimal has been well sampled, is there any circumstance under which you would want to use the greedy algorithm?
I mean, for our result, I think our pessimistic algorithm just dominates the greedy algorithm in the sense that when greedy algorithm can do well, we can also do well at the same rate. When they cannot do well, we can still do well. So I guess in that case, we probably always want to use the pessimistic learner. Yeah,
Okay.
thank you.
And my other question was, so you mentioned that the actions are the set of actions is finite.
Right.
Are they also disjoint from one another? I'm thinking about an application in which they might be different drugs.
Right.
Can you consider combinations of them as long as you're considering a finite number of combinations? Are they allowed to overlap?
I think so. I think so, but I think the formulation needs to be modified a little bit, but I think the framework can still go through. Yeah, thank you.
More questions? There are no more questions. We can thank Zhimei Ren for a great talk.
Thank you. Thank you.